China just unveiled two Starship clones, one copying SpaceX's exact stainless steel design and Raptor-style engines. But Elon Musk revealed why this will backfire. Full-flow stage combustion is so complex that even SpaceX blew up a bunch of engines perfecting it. What makes China think they can master what took SpaceX years of painful trial and error? China's Glacier 1 represents the most ambitious rocket copying attempt in aerospace history. But here's what Elon Musk understands that Chinese engineers are about to learn the hard way. Full-flow stage combustion isn't just difficult. It's a technological trap that destroys unprepared teams. The numbers look impressive. Glacier 1 stands 92 to 93 meters tall, weighs 1,100 tons at takeoff, and promises 42,000 kilograms to orbit. But here's what few people realize. These aren't just specifications. They're a blueprint for catastrophic failure if you don't understand the underlying physics. Picture this. SpaceX's Raptor engine operates like a perfectly choreographed symphony where every instrument must hit its note at precisely the right moment. Now imagine trying to conduct that symphony by watching a recording without understanding music theory, timing, or why each musician plays their part. That's essentially what China is attempting. The Mammoth 1 engine sits at the heart of this challenge. Like Raptor, it uses full-flow stage combustion, a cycle so unforgiving that Musk himself admitted SpaceX had to blow up a bunch of engines and melt more than a few combustion chambers before achieving stable operation. And here's the critical detail most overlook. Those weren't accidents. They were necessary education. Why would SpaceX accept this risk? Because full-flow stage combustion offers the highest performance possible from chemical rockets. But it requires two separate pre-burners operating at extreme conditions, feeding turbopumps that inject propellants into a main chamber where everything must work in perfect harmony. If any single component fails, the entire engine destroys itself in milliseconds. China's RTEC completed their first milestone on September 1st, a pre-combustion chamber fluid atomization test. This might sound technical, but think of it as testing whether they can light a match without burning down the house. The fact that this single test represents a major step from theory to real-world engineering reveals how early they are in a process that took SpaceX over a decade. And here's what's truly revealing about their approach. While SpaceX embraced failure as education, spending years learning why things break, China is attempting to skip directly to success by copying the end result. But you can't copy the knowledge that comes from watching your million-dollar engine explode and understanding exactly why it happened. What happens if their approach fails? We'll come back to this crucial point because the implications extend far beyond just Chinese rockets. But this technical gamble is just the surface. What's really surprising is how this copying attempt reveals a fundamental misunderstanding of what makes SpaceX actually successful. The emergence of Chinese Starship clones isn't just about technology, it's about a strategic miscalculation that reveals why true innovation can't be reverse engineered, no matter how much money you throw at it. Stargrid technology looks impressive on paper. Founding team from Tsinghua University, 60-plus employees with 90% holding master's degrees, CTO with 10-plus years aerospace experience. But there's a detail that exposes their fundamental problem. They've raised only tens of millions of yuan, roughly $2.8 million, for a project that will realistically need billions. This isn't just a funding gap, it's a philosophy gap. SpaceX spent an estimated $1 to $2 billion developing Raptor engines alone, with Musk publicly embracing each expensive failure as necessary learning. Chinese companies are betting they can compress this timeline and cost by copying visible results while skipping the invisible education. Here's what few people realize about SpaceX's real competitive advantage. It's not the stainless steel construction or methane fuel or even the full-flow stage combustion. It's their institutional tolerance for productive failure. While traditional aerospace companies, and apparently Chinese ones, try to engineer away risk, SpaceX engineers toward learning. But there's something deeper happening that most analysis misses. The second Chinese rocket, Wang-1 from Weightlite, takes a completely different approach using all-carbon fiber construction. This reveals that Chinese engineers understand they can't simply copy SpaceX's materials approach. They're betting that advanced composites can sidestep some fundamental challenges. Their 350-ton rocket aims for 9,000 kilograms to LEO with reuse. Respectable numbers, but here's what's noteworthy. They're not trying to match Starship's capabilities. They're trying to find an alternate path to similar economics. This suggests Chinese engineers recognize that direct copying has limitations. And this leads to a fascinating question that determines everything. In aerospace, what actually constitutes proprietary technology? SpaceX publishes engine specifications, live streams launches showing detailed vehicle behavior, and Musk regularly explains design philosophy on social media. Yet replicating these systems remains extraordinarily difficult for well-funded, experienced teams. The answer lies in what engineers call tacit knowledge, the thousands of small decisions, learned intuitions, and hard-won understanding that can't be transmitted through documentation or observation. When SpaceX engines exploded during development, engineers didn't just fix the immediate problem. They developed intuitive understanding of why that failure mode occurred and how to prevent similar issues in future designs. Chinese teams have access to SpaceX's public information, but they're missing this crucial institutional knowledge. It's like trying to become a master chef by copying recipes without understanding why certain ingredients work together or how to adjust when things go wrong. And here's why this changes everything. The outcome of China's copying attempt will prove whether aerospace innovation represents genuinely sustainable competitive advantage or whether sufficiently funded reverse engineering can overcome any technological moat. The technical realities of what China is attempting suggest we're about to witness one of the most expensive lessons in aerospace history about why breakthrough engineering can't be successfully copied without understanding the underlying principles. Here's what happens when full-flow stage combustion engines fail. They don't gradually lose performance or give warning signs. They explode, spectacularly. And here's the critical detail. SpaceX's years of explosions weren't just part of development. They were necessary education that can't be acquired any other way. Every Raptor explosion taught SpaceX engineers something specific about failure modes that can't be predicted through computer simulation. The way metal behaves under extreme thermal cycling, how combustion instabilities develop, why certain injector designs create problems. This knowledge exists only in the heads of engineers who watched their million-dollar hardware destroy itself and understood exactly what went wrong. China's approach assumes this knowledge can be bypassed by copying final configurations, but physics doesn't work that way. When their Mammoth 1 engines start exploding, and they will, Chinese engineers will face the same learning curve SpaceX navigated, except they'll be starting years behind with smaller budgets and less institutional tolerance for expensive failures. And there's a detail most people overlook about systems integration. Even if China successfully copies Raptor-style engines, Starship's success depends on thousands of precise interactions between propellant management, engine throttling, aerodynamic control, and recovery systems. Each component affects every other component in ways that become apparent only during actual flight testing. SpaceX discovered many of these interactions through expensive trial and error. Starship prototypes that exploded during landing, engines that shut down unexpectedly, heat shield tiles that failed in unexpected ways. Each failure taught them something that improved the next iteration. China is betting they can skip this learning process, but complex systems don't work that way. Here's the timeline reality. China's most optimistic projections put first flight several years away. By then, SpaceX will likely be flying improved Starship versions with capabilities exceeding anything China currently plans. This creates a permanent technology gap where China remains perpetually behind, copying yesterday's innovations while SpaceX develops tomorrow's breakthroughs. But perhaps the most important implication is what this reveals about innovation itself. If complex aerospace systems could be effectively copied, every major space power would already have Raptor-equivalent engines. The fact that nobody else has achieved similar capabilities, despite years of trying, suggests that true technological leadership creates sustainable advantages that persist despite information transparency. The broader space industry is watching this experiment because the principles apply beyond rockets. Whether it's satellite technology, space manufacturing, or Mars exploration systems, the question of copyability versus innovation determines how technological advantages spread globally. What makes this particularly fascinating is the timeline compression. Unlike historical technology races that played out over decades, modern development cycles and social media transparency mean we'll see China's success or failure in real time, providing definitive answers about whether breakthrough engineering can be reverse engineered. The ultimate irony? By attempting to copy SpaceX's most complex technology, China may inadvertently validate Elon Musk's most important insight, that in cutting-edge engineering, the willingness to fail fast and learn from failures creates more sustainable competitive advantage than any specific technical configuration. In the end, China's Starship clones represent more than ambitious rockets. They're a real-world test of whether true innovation can be shortcuts or whether breakthrough capabilities require walking the difficult, expensive path of original discovery, complete with all its spectacular failures and hard-earned wisdom. This is exactly why Elon Musk's fail fast, learn faster philosophy represents the real breakthrough, not engine design or materials. China's attempt will likely fail because their shortcuts the most valuable part, education from expensive mistakes. What this means is profound. True technological leadership isn't about visible innovations. It's institutional knowledge from productive failure. This creates advantages that persist even in our connected world. Over the next 2 years, we'll watch China's engines either explode or succeed against engineering logic, answering whether breakthrough technology can be reverse engineered. Meanwhile, SpaceX pushes toward Mars missions, requiring unimaginable innovations. How do you think this plays out? Will institutional knowledge prove impossible to copy, or can funding overcome any technological moat? This is Space Hub. We dive deep into breakthroughs shaping humanity's future beyond Earth. If this analysis helps you understand the real forces driving space innovation, you know what to do. The next decade determines whether space belongs to first movers or fast followers. The answer reshapes how we reach the stars.